Good morning or good afternoon, everyone. Welcome to the next edition of the CAE Department Seminar Series. I'm delighted to have with us Professor Matthew Gombeda, who is going to talk about facilitating the next generation of high early strength concrete mixes for precast construction. Dr. Gombeda is an assistant professor of civil engineering and the director of the Structural and Concrete Materials Testing Lab in Civil Architecture and Environmental Engineering at Illinois Institute of Technology, IIT. His major research areas include behavior and mechanics of reinforced and pre-stressed concrete, innovative precast concrete components, mechanical characterization of high strength concretes, blast design and analysis methodologies, among other topics. He's also interested in the development of codes and standards. He's an active voting member of multiple PCI technical committees and of multiple ACI committees. He serves as the vice chair of the PCI Research and Development Council and also as chair of ACI 377. Thank you very much, Professor Gombeda, for doing this, and the stage is all yours.
All right. Well, thank you, Prannoy. I really appreciate the opportunity to be here today and present some of our work and talk about the need for developing a new and next generation higher strength concretes for precast construction. A lot of the stuff that we'll talk about today, kind of as I was telling Prannoy earlier, bridges the gap between material science of concrete and the larger scale implications for structural design. And that intermediate area has spawned a lot of interesting research, a lot of interesting conclusions, and is something that I really encourage other structures faculty to have the appreciation for the materials, or structural engineers in general to know the properties of the materials when they're designing structures. So I feel really passionate about this topic and walk you through some of the stuff that we've worked on recently. So just a little bit about me to start with. Let's see here. For some reason it's not letting me go forward. One second.
No worries.
Okay.
Let me try the page down.
Let's see. Okay. Can you see it now?
Yes.
All right. Okay. So
Perfect.
just a little bit about me. Prannoy gave me most of the introduction, but I will show you here again. So I went to Lehigh for grad school. I went to Penn State for undergrad way back in the day. Work mostly on concrete structures and materials, but a lot with applications for precast and some blast design and progressive collapse stuff previously in my graduate school and even a little bit today as well. And just give a little bit of an overview of our lab space here in Chicago. So here is the one half of the lab that we do a lot of our materials testing on. If you look in the back there, you can see our relatively large planetary concrete mixer. We can do about 4 cubic feet at a time when high shearing action, and it's really nice for things like UHPC and for SCC and to make a lot of specimens from the same batch to reduce variability, curing chamber, storage of aggregates, and all the requisite compression machines and grinders are off to the right there. And then here is a photo of the other half of the space, which is our high bay, which includes a post-tension precast reaction floor and buttress wall that we designed and erected ourselves, actually. And on the right is a 800,000 pound universal testing machine that we use pretty heavily for some of our tests, as you'll see later. And here's just a picture. I like to show it as we were erecting the reaction floor, and it's kind of funny because Stan is our one of our shop technicians, and the going joke was that he was just sad because we were taking over the lab with all this new stuff, but in reality he was looking at a little bit of damage on the door, so he was actually quite happy that day. But anyway, so let's just a quick outline of what I'll cover today is I'll do like a brief overview refresher for precast concrete for those that might not be as familiar. I'll talk about some of the work we've done on high volume fly ash concretes with high early strength, a little bit on concretes for precast that were driven by high early flexural strength as opposed to high compressive strength, which is commonly done in a lot of cases. I'll also touch a little bit on our work on non-proprietary UHPC and the strength development and the relative early age window that we had with those mixes. I'll talk about some of my involvement that relates to a lot of these areas on the design recommendations and design standards across PCI and ACI. And then I'll talk a little bit about what I think the future research needs are and some potential collaborations that I'd like to explore in the future. So what I'd like to do now is get into just a quick overview of precast concrete. And the most simple definition I can give is when you're fabricating a structural or architectural component in a location other than where it's going to be in its final position. So it can be tilt up, which means that you are building on site and then it's just cast on the ground and you literally tilt it up and it stands up as a wall and it's now part of the building. It's not done in a factory, but they use ready mix trucks and they cast it right on the ground at the job site. There's also factory precast over on the right where you have it in controlled conditions. It's indoor and you still have to lift it and move it into position, but now it goes on a truck first before it goes to the job site. And here's just one example of a specific precast component that I've worked a lot on. It's called a precast insulated wall panel. So it's got two concrete whites, which can be pre-stressed or non-pre-stressed, but mostly pre-stressed. And there's a layer of insulation in the middle that helps improve the R value thermal resistance of the wall. But in order to make the wall behave compositely and have benefits for checking stresses and deflections, we connect the two concrete whites with connectors. And those connectors are usually made of polymers to help further reduce the transmission of thermal energy across the structure. And I've done a lot of work on the testing of those connectors and developing design standards for insulated wall panels in general, which I'll talk a little bit about at the end. And so now let's talk about the connection between high early age strength and precast. So in traditional cast in place construction, we see something like on the left where we have formwork and we have the concrete cast and it's in its final position. It never has to move and it never has to be lifted out of place. Okay. But versus if we're doing precast, right, we have to not only now cast it in a bed and then lift it out, we have to do it very quickly. And the reason that we want to do it very quickly is because it's a business thing. It's an operational thing. The more precast components they can make out of a single casting bed, the more efficient from a financial perspective the business is. And we're talking about within 24 hours on most occasions, probably even less most of the time. And we also have to apply for pre-stress members, the pre-stress strands have to be released before we can remove it from the formwork. So now we have to design for early age compression as the pre-stressing is applied. And we also have to design for early age flexural strength because when the member is lifted out of the bed, it wants to deflect under its own self-weight. And generally, the number that people have targeted is 3,500 PSI compressive strength within 24 hours or less. And that number has only gotten more stringent as they try to be more efficient with different designs. So it's kind of like a baseline minimum at the very least. So I'll walk you through some of the projects here. There's a lot of information and I'll go a little quickly, but if you have questions at the end, I'll be happy to take them. So the first one I want to talk about is a project that we had funded from DOE back starting in 2020, which is high volume fly ash for high early strength concrete mixes. It was a collaboration. IIT was the lead, and then Penn State and Lehigh were also involved. And the goal of this project was to increase the beneficial use of fly ash by at least 15% in precasts. And the reason that there's been limitations for having higher uses of fly ash or other SCMs is because we really are sometimes at a disadvantage with early age strength gains when we have materials that have lower heats of hydration. So there's been a cap, like about 25% for many years of fly ash because they were worried that you couldn't get the higher early strengths if you went higher dosage of fly ash. And we wanted to change that narrative and find other ways to get the early strength even with more fly ash. you could kind of see here an example here where typically, we're using type 3 cement traditionally in precast mixes, and you get that really high rapid strength gain early on. But when you start to replace that type 3 with larger volumes of fly ash, you start to get lower strength gains. Like you see that curve down below, the curve is going to be similar more to what you would see in like an old school type 2 or 1-2 cement at higher dosages. And you can also see here the effect that another study that we did as part of a literature review, where that solid line on both curves is the control, it's the same mix. But when the dosage of the fly ash is going up from 20 to 40%, we see a significant reduction in the strength gain over the 0 to 28 days. But specifically in the early age window is where we're most concerned about, as we talked about earlier, which this study didn't even really zoom in on that area as much as we wanted to in our project. All right, so what did we do? So the first thing that we did was develop what we called optimized binders. So we had increased from 25 to 40% fly ash, and we had looked at using a fresh class C and F and also a landfill ash from Pennsylvania, and different optimization strategies with the dosages, but also some gypsum optimization that I'll talk about in a little bit, and some admixture optimization. We looked at binary binders, but just the type 3, because back in 2020, 1L was still not really the common thing on the market yet. So it was mostly type 3 and the high volume fly ash. And we also did some ternary ones, which actually didn't seem as promising. And we moved forward with the binary options. And here's kind of how we narrowed down which ones we wanted to look at just from the mortar cubes at this point. Our goal was 4,000 PSI compressive strength at 24 hours of the mortar samples, knowing that if we scale it up to a concrete cylinder, we have a little discrepancy in strength there. So we wanted to be conservative when we started looking at these results. And there's, like I said, a lot of data here looking at different accelerator dosages and different types of fly ash, like I said. But the key takeaway is that we were able to exceed our goal of 4,000 for a lot of these different options that then helped inform what the concrete strength looked at. And I should also note that this part of the study was done by Penn State in collaboration with us at IIT. One thing that was crucial to our dialing in our strength development was gypsum optimization. So when we're adding more fly ash and we have a reduction in Portland cement, we're losing a little bit of that gypsum content that could help balance chemically the mix. So we're adding back in the gypsum to an optimal dosage to facilitate the strength gain that is most effective with our dosages of cement and fly ash at 60% cement and 40% fly ash, essentially. A little bit of gypsum that we'll add here in addition. So this process basically looks at different trials of gypsum dosages and finding where the peak compressive strength lies with regard to how much SO3 content is added into the binder. And you can see for the different types of fly ash there, we were able to determine what that optimum value of SO3 was. We also then did another study on accelerator optimization, used a few different products, and then basically narrowed down the dosages of those to, again, help to inform the effect on strength gain. So now here's where it was handed over to us at IIT after coming from Penn State. We were then scaling the concrete in larger batches. You can see a lot of flexural strength specimens, modulus of rupture specimens there. In our curing chamber there on the right, you see cylinders as well. And we're focusing on early age properties. So we did 12, 18, 24 hours for the most part. And then we also did 28-day breaks just to be able to compare to the standard time frame for compressive strength testing as well. And here's a picture of our finished SCC mix in the wheelbarrow, or one of them anyway, straight out of the mixer. And so here's some results for compressive strength. So we had, again, the minimum goal was 3,500 at 24 hours. And wherever I have the light green is where we've hit that target. So for some of the mixes, actually for a fresh class F and actually did some type 1L mixes towards the end of the project as those cements were starting to replace the old type 3, we were able to hit our target within 16 hours in a few of the mixes. An average of 3 cylinders here gets us the results in the table. And then for all of the other mixes, most of them anyway, we were able to hit our goal within 24 hours and a lot of them within the 20-hour window. And we're not using any heat to accelerate the mixer. It's purely based on the mix design optimization and the accelerators. We then also went to do flexural strength testing to help inform like the things for like calculating the cracking moment to make sure we don't crack the member when it's lifted out of the casting bed. And you can see here the results for those tests. The more interesting way to look at it, I'll come back to in a second. The more interesting way to look at the data is sort of plotting it over time to look at the strength gain. And what we tried to do here was basically extrapolate the data points that we had to form these curves that could help generalize for these types of mixes what the strength gain profile would look like. So if you had a specific compressive strength target, it could help in like the preliminary mix design stage for a precaster to estimate approximately at what age they would be able to get that value. Now, it doesn't replace testing in a plant. They're still going to have to do it for their own mix, but it was sort of a preliminary thing that could help inform how to hit those early strength targets. And you can see it here for the different types of fly ash, and also at the end, like I said, we included the 1L cements. Now here's an interest. I like this plot because when we relate modulus of rupture, typically it's done by taking the square root of the compressive strength, and the factor in front of it from the ACI code in chapter 19 is 7.5 usually. And so forgive me here, they're in metric units. The number is 0.62 in metric instead of 7.5, but you can see here we plotted for the different mixes to determine how conservative or unconservative that ACI equation was for 2 reasons, right? Because we were changing the mix design. We have different properties now, but also that equation is largely initially developed at later ages. So we're trying to actually see how the early age behavior also is characterized in this sense. And we found that most of the time it was conservative, which is safe, but also in terms of dialing in the efficiency of the precast plant, the ability to do flexural testing on your own can help get a better idea of exactly when those performance targets are hit. The other aspect of the story then was how to then take these results and scale it up to structural design. And we came up with this framework here that is in another paper that my student and I published that looks at how to use different methods using both the plots of age, concrete strength versus age that I showed earlier, but also now incorporate in some maturity testing to monitor the temperature in the concrete to help correlate the strength gain properties in the member back to what we had when we did the tests on the specimens in the first place. So we did some larger scale tests with some inverted T-beams, and our lab is kind of like a mini precast plant. So we were able to actually fabricate everything in-house and test it in the same space. Kind of a little unique thing that we can do here. But if you look closely, you can see there's a maturity sensor on the far end. So it's monitoring, like I said, the temperature in the concrete. And then one of those sensors is also put in a cylinder when you do the test for the compressive strength. And then you can correlate the temperature for both specimens, and we can have a information that helps tell us predict what the strength in this beam is before we even test it. And here's the beam in the test setup. And here you can see the failure load or the failure mode of the ultimate moment capacity. And then here is just looking at the test data versus some predictions from that framework that we developed. So when you use maturity versus when you use just the concrete strength versus time, and when you do actual modulus of rupture testing, you're going to get slightly different estimates of how you can calculate the cracking moment of the beam, which is something that we focused on because, again, with early age lifting and handling, it's a primary design objective in precast. So our comparisons are pretty close. They're a little conservative, but they're within a reasonable amount of error, and we felt confident in our framework and the underlying method that used to predict the cracking moment strength. So the next project was funded by ACI Foundation back in 2022, and I worked on it with a colleague of mine at Urbana-Champaign. on highly flexible strength concretes for precast. So this one, the objective was to evaluate the progression of highly tensile strength or highly flexural strength in non-proprietary high strength concretes that were specifically developed to have that enhanced flexural strength. In the past, we're so used to, let me come back to that one, right? We're so used to this equation down below where we have a set compressive strength and then we're asked to calculate the flexural strength as a result of that number. But we wanted to move towards like a performance-driven flexural strength mixed design approach so that we can target a specific number of a modulus of rupture at about 750 psi at about 18 hours. And typically you can hit that number with like UHPC or really high strength concretes, but we wanted to create it in a mix that would not have the difficulties or the added complexities of UHPC and also wouldn't exactly tie it to that compressive strength of about 18,000 or so. So it was really like performance specifically targeting that flexural strength. Again, great for the precast industry, also great for things like tall building construction where they need to keep moving up floors and release shoring and that sort of thing. So there were, again, trial binders that were started. We generally start from the binders themselves and then scale to concrete and then go to structural testing, as you'll see again here. Particle packing was a big part of this work, and my colleagues at Urbana led that effort. And they also introduced this term particle packing density to assess the difference of the densities of the customized matrices from like an ideal curve, for example. And then they used software to basically look at how to visualize these analyses and help inform how that the particle sizes would be useful in different trial variations of the binders for the concretes. So here you can see the particle size distributions for some of the materials with a fine aggregate with the ASTM C33 limits, also for the coarse, the 1L cement, and then some of the SCMs that were used as well in the bottom right. And then here's the resulting mixes that we did. Forgive the numbering, but there were trials before 6 that didn't make the cut. So 6 and 7 were the ones that we moved forward with, and you could see the relatively high particle packing density above 90% for both of them. And it's doing a pretty decent job of hugging that ideal curve from the ANA model, which is why we decided to move forward with it. You know, it's always a balance, right? We want to develop things that are theoretically as correct as possible, but also understanding that using things like local materials and standardized equipment is also going to change how far you can push these efforts. So it kind of is a break-even point of how we can optimize our results. And here are the mixed designs. So I won't go through it all, but we basically had 2 variations of the M6 one with different dosages of an accelerating admixture. And the second one, we also had a third one that was applying heat to help further expedite the flexural strength gain. And then the last one was using silica fume as a replacement for Class C fly ash. Here's some workability properties that we measured from the testing that we did. All of the slump flow target was to get SCC performance, so we're at or above a 20-inch slump flow in each of those cases, which was satisfactory for us. And then we look at the early age modulus of rupture performance. So our target was, again, 750 at 18 hours. We got pretty close. It wasn't easy, but we were able to get 722 in the heat mix, and we were able to get over 700 in the first M6 mix. And then as we start to get to 21 hours, we start getting really close to that target, and then we're surpassing that target pretty easily at 24 hours. So while we didn't exactly get it at 18, we got it pretty close. And there still can be tweaking that can be done to even push it over that threshold, and we're still working on some of that stuff. Just to give you an idea of what the corresponding compressive strength was, we have like at 18 hours or whatever, we have 47 MPAs. So somewhere about like less than 7,000 PSI, high 6s, right? So we're hitting these targets that normally we would hit with much higher strength concretes, but we're in the 6 or 7,000 PSI compressive strength range corresponding to these things, which shows that difference in the correlation of those 2 values. And here you can see the plots of, I like this chart, right, where you plot the modulus of rupture normalized to the square root of the compressive strength as a function of the age. And we'll pay attention to the one on the right because 7.5 is the code equation. But when you look at a lot of these mixes, especially as you get closer to 24 hours, they're much higher than 7.5. And you might look at it and say, well, like, oh, it's 7.5 versus 9 isn't that much. But when you actually do the numbers and look at the stresses, it does have a pretty substantial benefit for the precast industry. So it does make a difference. Even if it's a little bit conservative, there's still some room to kind of dial it in a little closer. And then here's some testing we did on modulus of rupture, which basically just shows that the ACI equation for MOE, which is 57,000, is a little bit unconservative in a lot of these mixes that we did here, likely due to even some of the aggregate properties and whatnot. But I don't want to alarm anybody here, but basically one of the suggestions is like if you're going through all this trouble to do the flexural strength testing and compressive strength testing, it's not terribly more difficult to also do the MOE testing, which is going to help get better estimates for things like deflections and stiffness when needed as part of structural analyses. We did structural testing on that one as well. Again, something we fabricated. So my students work on putting the rebar cage to get reinforcement cage together, and we do all this stuff in-house. So we kind of pride ourselves on the ability to do all that stuff. But and it was heat cured. The beam was heat cured, as you see there on the right. And then here's some photos of the test. And we had basically used the properties that we had generated earlier into an open source component level fiber beam column element model and predicted the results. And generally speaking, it's a pretty decent match. Once you start to get past the like the yield point or whatever in a structural concrete, matching becomes more and more difficult. So with more work, we'd fine tune that curve, but in general, like we were able to show that we're in the right ballpark and our peak strength is within some reasonable amount of error of basically taking those properties in the calculations and predicting the test results. And here's just another example on the stiffness side as well, with a reasonably small percent error in the tangent stiffness from the test and the theoretical stiffness when we calculated it from the E that we measured in the test and the gross moment of inertia. And then the last project here that I'd like to talk about is our work in the non-proprietary UHPC, again with Urbana-Champaign. This one is funded by IDOT. So I'm sure most people here have an idea what UHPC is, but we always give this general slide of what it is and shows this nice pretty curve. Great, but I like to kind of just refresh everybody with the minimum definitions for strength. So ACI 239 says in that it's compression, it's used to be 22,000, but in recent PRC it's come 17,500, which is consistent with what Federal Highway also specifies in their documents. Now on the tensile side, we have the ability to take advantage of the increased tensile strength and also tensile ductility when we have steel fibers included. And what the 239 now says is that the direct tensile strength should exceed 720 psi basically, and then Federal Highway says the effective cracking strength in direct tension, basically what the strength of the UHPC specimen is before it initiates cracking, before the ductility kind of really takes over, is about 750 psi is that minimum. But the current obstacles are not so much on the strength side. It has a lot to do with the proprietary nature makes things more expensive, and non-proprietary mix designs require a little bit more thinking and frameworks. There's still a little bit of a relatively high cost associated with these mixes. Mix times are too long, and the workability retention is a huge issue. With the flow being met right out of the mixer is one thing, but then you come back 10 minutes later and we get things like skin formation, and this mix really starts to have it starts setting very quickly and it's hard to finish which is a problem. So what we did is we basically re-engineered some of these mix designs for non-proprietary mixes to be able to be used with local materials in Illinois. And it started on a benchtop scale again with the small cube specimens using this mixer here. And we developed this method of when to add the materials, how long to spin the mixer, and then how to evaluate the performance at different steps before we get to the bottom where we would discharge and make specimens. But that one was ultimately then superseded at the larger scale when we went up to the bigger mixer. And you can see it's very similar to the framework, but it's a little bit different because we went to dial in how the larger quantity of concrete affects this work and the different type of mixing action and those sorts of things. And so what we did was we got these results for a couple different variations of the UHPC mix. So we have one that is chamber cured in accordance with C511. We had one that used a class F fly ash that was sieved through number 200 to emulate an ultra-fine fly ash, which was part of the original development. We recognized that not everybody had access to the ultra-fine fly ash, so we wanted to come up with an equivalent way to produce it with the standard fly ash. And then we also had the dash A ones are what they were done ambient. So some of these members you're not going to have the luxury to do in a chamber. So we wanted to also look at the variation in the strength when we had ambient conditions versus ideal conditions in the chamber. And you can see the compressive strengths here, the cube specimens in the table on the left, and then the cylinder specimens there on the right that we did at the larger scale, the last three of which had the 2% steel fibers in addition, and the first ones that we did and the cubes did not in this case. So just a little bit of looking at the variation here. So the average of the specimens done at the 3x6 scale versus the cubes were within about on average 6% difference. And again, there's not fibers, but also we recognize that the fibers don't have a substantial role in the compressive strength. We're not evaluating tensile ductility right now, but we just wanted to make this first comparison. Now, if we take it a step further, if we look at the ambient conditions, the first one, the 6% is the one that was done in the chamber for the smaller scale, and then ambient conditions at the larger scale. But if we compare the apples to apples with both being done in ambient conditions, we see less than 1% difference on average. So we were really satisfied with how we were able to get the compressive strength values to reproduce at the larger batch size. Here's an interesting study that we did that looked at calculate some of the statistics. So the goal here was to calculate the coefficient of variation considering all these different variations that we did in the mixes. So the first column is all of the different mixes with the different scales, the cubes and the bigger scales, and all of the different changes in the fiber dosage and all that stuff. So there's not consistency there, but it's done on purpose to just see what the overall COV was across everything. And it was about 7%, which isn't terrible. When we just do it at the stuff that was done in our lab, all right, the initial one was done at UIUC. When we look at just everything done at IIT, it was reduced to 4%. When we look at everything that include just the standard Class F fly ash, it goes down to 2.8 as opposed to the U one, which was the sieved version. If we go then to just the mixes produced at the larger scale with the 3x6 specimens, we're at 1% COP. And we get 1% again if we look at the variation with those that were produced with steel fibers only. So the COVs here are actually really good across all these slight variations to get a standard characteristic average value without much deviation for all these different mixes at different categories here. And then we did the tensile stress strain testing with AASHTO T397. We used a manual grip setup because we didn't have a machine that had hydraulic grips large enough to accommodate the 2x2 specimens. And we wanted to also kind of adapt this method to labs that maybe had similar issues where they didn't have a ton of extra equipment to do these tests. So you can see here on the left, there's a specimen loaded in the machine. It's got the grips at the top with 4 bolts. Those are tightened at 30 foot-pounds of torque using a manual torque wrench to ensure the right tightness. And then you can see there's a transducer there that'll measure the displacement at the middle of the member that we can then calculate the strain from. And you can see here on the right, after the test, if you do the test right, you get this crack right in the middle of the gauge length of where the transducer is. And then here's a plot of the tensile stress versus strain across specimens that had the same mix design, but they were done from different batches, again, with the goal of demonstrating like consistency and reproducibility and mixing them many times. So we saw pretty consistent trends of our tensile stress strain curve. And this one's only plotted up to 1% tensile strain, which is pretty good. Much higher remaining stress that you'd have versus a normal concrete, obviously, and thanks in large part to the steel fibers. And then we made some beam specimens with these mixes. So we tried a couple different variations of a rectangular section. The one in the top left did not have any shear reinforcement, nor did it have any of the fibers, and we got this really dramatic and clean looking shear failure, which was pretty crazy to watch in the lab. But when we did it we added the stirrups at the minimum spacing or the maximum spacing for ACI 318. We then added in the fibers, and we got this really clear isolated flexural crack failure. And then the C is when we removed the stirrups, we actually found that for this mix, if we didn't use the stirrups, the 2% fiber dosage was enough to handle the resistance for that internal diagonal tension that caused the shear failure in the first test. So it's really showing that the shear reinforcement wasn't needed from a behavior perspective. You may still add them for structural safety and reliability, but from a pure behavior perspective, it wasn't needed in this case. And you can kind of see here's the plots of the different responses, and the ductility becomes evident, like in the first one, which is the NNTR0, which is the orange curve, which drops very suddenly. The one in the bottom is also interesting because we showed for the 2 specimens that had the 2% fibers, we tried to match with a computational model. Again, the tensile strength data and the compressive strength data was input into that model, and the complete model overshoots the test a little bit, but also I wanted to bound the results by showing the one in blue is when we neglect the concrete tension. So the results here are telling us that the experimental result is bounded by the complete model, where the tension is engaged perfectly without any little defects in the beams or anything that could cause it to be slightly lower strength. And then the blue curve is where we wouldn't have any tensile strength considered at all. So we're actually bounded nicely between those 2 curves, which I thought was a favorable result. Here we then sought to develop an I section, a more efficient use of materials. And it was done really thin. It's like 1.5 inches thick in the web, which you couldn't do with standard concrete. And the idea here was to compete with like a structural steel section. The I section is 50% of the cross-sectional area of the 57% of the cross-sectional area of that rectangular one, but the flexural strength when we ran the computational model gave us about a 20% or so boost in strength. And here you can see some photos of us fabricating mold. I have my students become carpenters and make formwork. I really like them to get hands-on experiences with these sort of things. And there you can see the I section that was cast. And here it is during the test. We put some blocking in there to eliminate the local bending in the flanges under the load and under the supports. And then here you can see the comparison of the test in the black curve with the full model that we had earlier in using the same computational modeling approach that we used earlier. And the peak strength is almost a perfect match. There's a little bit of a discrepancy in the post-peak behavior and the stiffness past the proportional limit, but in general, from a strength perspective, we were quite pleased with the comparison with the results. So those complete the projects. I'll do a little bit now on my involvement. So I was one of the authors on this PCI standard that was released in 2020, early 25, I think, on the design of precast insulated wall panels. And I've also been heavily involved on the development of PCI 319. I was also on the design standard committee of PCI that helped develop the new precast code and the insulated wall panel one. I also serve on 318 subcommittee D, which is structural members. Basically helps to inform chapters. I think it's like 7 through 11, I believe, in the ACI 318 on beams and two-way slabs and columns and those sort of things. I've also worked on revising this document for Committee 232, which is a report on high volume fly ash concrete for structural applications. And then I also was a lead author on Chapter 5 of this ACI 377 report, which was precast and pre-tension floors for collapse, resistance, and structural integrity in buildings. And as Prannoy mentioned earlier, I'm currently the chair of 377 that we focus a lot on things like progressive collapse and general resilience of concrete structures. And then a lot of my other work, especially back in grad school days, is on blast design. So I've been still heavily involved in PCI blast committee and also a member of ACI 370 with the concrete structures for blast effects. I'll get into a couple research needs and collaborations. I do want to just give a quick shout out. I talked a lot about PCI, and I was talking to Prannoy earlier, is that PCI is going through a phase now. We're sort of increasing our research awareness to people that have not been involved before. We have a lot of needs in the precast industry that are very much centered on things like materials and different types of AI and those sorts of things are emerging as well, and robotics and even industrial engineering and really what I'd like to see is more younger faculty become engaged at PCI. I recognize that people can only do so much, but at the same time, I think there's a lot of people out there with good expertise in early age strength and reactivity testing and durability that would benefit from their involvement at PCI. So I'm the vice chair of the R&D council there. I know we're going through some changes there, and we're exploring ways to have more funding opportunities as well for young faculty and others to get engaged. And I will share that information as it comes along in the future, but I just wanted to give a little plug about my experience as a PCI have been favorable and encourage others to get involved as well. It's very parallel to ACI. It's not a trade organization by any stretch of the imagination. It's heavily developing standards and design recommendations and a lot of active research going on. So I encourage those who are interested to reach out to me if you have more questions or are interested in getting involved at PCI. Future research needs. So here's just some of the things that I have come up with over the years. So there's still a lot of work to be done with early age strength and concretes made with latest or novel cements. Looking at potential implementation of what the next generation of 1L cements looks like. I know I've heard about 1T, which is ternary blends of cement of the Portland limestone cement, and also an HE version potentially that's still kind of not widely used. We're still looking at the production side or the implementation side of the non-proprietary UHPC mixes to reduce mixing times, make it more finishable, those sorts of things. Looking at performance-driven design of pre-stressed members at transfer. If we are able to increase the early age strength is one way to solve the problem, but also if we're able to do more detailed analyses of how to achieve the stresses in a pre-stressed member at early ages when we release the strands, it's also going to benefit us. Any innovative precast design solutions are fair game for me. I also have an interest to 3D printed concrete with more complex states of stress, such as if you were to precast it and had to lift it and pre-stress it, those sorts of things. And then any kind of experimental test methods for concrete materials and structures. So concludes my presentation. Happy to take any questions or feedback, but I'd just like to thank everybody for listening and Prannoy for this opportunity here to present today.